So problem set 2 is up. It's about, it covers a sculpture, a type of sculpture that I've seen them in a couple places. It's a giant ball, a granite ball, sitting in a granite support with water between the two. So it turns essentially without friction. Friction really is a major focus today, but this is a system that tries to get rid of friction. Once they get rid of friction on, even though it's this gigantic ball, you can get it spinning, and you can do, spin any which way. So they're cool sculptures. I hope you find one somewhere. Yeah, I've been to the Richmond Science Museum for too long. I somehow remember there being one there, but anyway, whatever. So hopefully you'll find it an interesting problem set. If you don't understand what it's talking about, go look up. I name it. It's a Kugel fountain. You can find it on the web easily enough. All right. Where things left off last time is just trying to introduce the story of friction, tell a story of friction. And sort of a useful thing to think about is the following demonstration, or it's hardly a demonstration, just something you've seen your whole life. And watch what happens. If I get this wagon moving, the wheelless wagon, and then have it move across the desk, it skids to a stop. And the question is, when a box skids to a stop on a motionless table, that being the box, what work is done by those two objects? Okay, there's work being done, or maybe not, or which one? So I've given you 5 choices this time. Think about, I'll give you a minute to think about it and talk with each other, try to figure out who's doing work on whom, or negative work, or no work. Okay? Give it a try. And as I say, you're welcome to talk to each other. Okay. Let's give it a shot at voting. How many think that A, the table does negative work on the box? That's the only thing going on. Okay. How many think B, that the box does positive work on the table? Okay. How many think both objects do positive work on one another? How about both objects do negative work on one another? D. And how about E? The box does positive work on the table does negative work on the box. Okay. Very thin on everything except the last one. E, people are voting for. So let's take a look at that. For the box to do, let's start. The table does negative work on the box. Let's try this first. Well, as it's skidding across there, the box was slowing down. The wagon was slowing down. So it was heading to the right. Something was pushing it to the left to cause it to accelerate to the left and slow down. That something was the table by way of friction. So the table is definitely pushing the box to the left with a frictional force. So far, so good? So the table exerted a leftward force on the box, and the box moved rightward. That's negative work. The table exerted a force that way, while the box moved that way, opposite the force, negative work. So the table definitely did negative work on the box. So far, so good? But that includes, actually, several of the answers allow that. Choices allow that as one of the answers. How about the box does positive work on the table? Well, again, with the story of friction, the table pushed left on the box with the frictional force. Newton's third law says the box had to push right on the table. And it did. So there was a rightward frictional force on the table from the box. That's certainly there. The issue is, did the box do work on the table? Because that's what E claims. What does the table have to do for the box to do work on it, apart from have a force acting on it? Move a distance in the direction of the force, right? Did it move a distance? I mean, apart from like a zillionth of an inch, did it move a distance in the direction of the force? No. I mean, we can quibble about whether it moved at all or just a tiny bit, but basically it didn't move. The box did not do work on the table. Questions about that idea? This seems to be violating all the rules I ever told you. The table is doing negative work on the box. The box is doing nothing on the table. So where did the energy go? Basically, the box lost energy, and it's gone. It wasn't exchanged with anything. Nothing's got it after it's all over. Well, it's there. It's just ground up into little bitties. It became thermal energy, so which is a thing to talk about in the context of wheels and stuff. Because most of what wheels do is not to get rid of friction, but to get rid of the production of thermal energy by way of friction. You don't want to waste precious energy that you have in, say, the motion of the car, or the gasoline in the tank, or the batteries, the electrical energy in the batteries. You don't want to waste that making thermal energy. So this is the strategic use of friction, not the elimination of friction. And friction in this case is destroying useful energy and making thermal energy out of it. Yeah, Fiona.
How much movement would the box have to do for it to be considered work?
So Fiona's question is, how much movement would the box or the table have to do in order for it to be considered work? That's a question of the context in which it is. In this case, the movement, for all practical purposes, you would never see the table move enough for the box to do any significant work on it. What's significant? If you're measuring it in joules, and it's 0.0, how many zeros do you have to go out there before you start seeing numbers? And you go after, you're about 3 or 4 or 5 or 6 zeros out there, we're not interested anymore. It's like, how much money did you make this summer? One billionth of a penny. That we're gonna call that 0. Is that okay? So there are occasions when I ask you a question, a problem set, and I have not nailed down whether I'm talking about 0 to all digits or 0 out to 17 digits and there's a 1 out there. I hope that it's easy enough for you to judge that I'm not talking about that 17 zeros and a 1. That's, for all practical purposes, that's a 0. Nobody would ever care about that 1. Is that okay? I occasionally mess it up and have it so that technically one of my answers is not right. I'll give you the classic example that I've encountered this before. When I bounce a ball off a wall, it bounces back. Baseballs, just for your information, are lousy at bouncing. When it bounces back, if I had a basketball, it bounced more nicely. Part of its difficulty in bouncing off, in stopping on the wall. Actually, this is part of another story I've told other people already. You go to the amusement park or the state fair, and they have all these games that you can play for only $1 or something like that, and you can win a stuffed bear that's this big, whatever. Those games are all rigged against you by physics. It's very unlikely for you to win most of them. The ones that you have any decent shot at winning, the bear costs 37 cents wholesale. So I mean, it's a total. These are excellent money-making systems based on physics. A lot of the games involve trying to get something to stop on a rigid surface. Like, instead of having just a wall here, suppose I have a wall with a wicker basket. Have you ever seen these games? There's a wicker basket there, just tilted just enough that you can get a basketball to sit in there if you're really careful. And you have to stand back here and throw the basketball into that basket and have it stay. Is this familiar to some of you guys? Right? It's rigged against you how? It's a rigid basket and a rigid wall. You cannot do work on it for all practical purposes. I mean, okay, if you go and push on it with a bulldozer, of course you can do work on it, but even yourself pushing, it's going to move a billionth of an inch for sure, and probably more. So you can do work on it, but that works so far down into the details. For all practical purposes, you can't do work on it. The result is the ball comes flying in there chock full of energy in its motion, and it can't give any of that energy to the wall. It's busy, it's got to do something. So it bounces. It bounces back out of the wicker basket. I mean, that's an oversimplification to some extent, but that's a real problem. It's very hard to get it to stop in there unless you can get it to waste its energy by way of friction, typically. You give it the right spins can get it to go in there, just to have it just wear out its energy and to turn it into thermal energy and stop. But otherwise, it's tough. And next time you go to a place that's got those games going, look at all the bouncy things, the rigid plastic ring you have to get over a glass bottle. You can't move the glass bottle with the ring, so you can't do work on it. You can't get rid of the energy in the ring. The ring just wants to keep going. All right? Lots of them. So, long story out of a question, but I will try as best I can all the questions I ask you to make it clear whether I'm talking about 0 or 0 for all practical purposes. Questions about that idea? I'll do my best. If I write the questions so that they cover all the contingencies and ambiguities, they end up this long and you can't remember what I'm asking you. It's tough. It's the world of lawyers, alas. They have to have all that boiler, all the little lines in there to cover all the contingencies. All right, so where did the energy go? It's wasted as thermal energy, and this brings up an observation that there are 2 major forms of friction. It turns out there are more than 2, but there are 2 that most of us pay attention to. You may pay attention to only 1, but there are 2 that are significantly different, such that it's worth knowing the difference. Sliding friction is the friction between 2 surfaces that are actively sliding across one another. Like, that's sliding friction, those 2 are. Now, if I try to pull this thing, and I don't get it started, I'm just pulling a little bit. I'm pulling to the left, I really am, and the wagon is not moving. So something is canceling my leftward force. That something is a frictional force from the table. I'll stop because this is tedious. The frictional force from the table was pushing the box to the right, but there was no movement occurring. And that's called static friction. Static being, nothing's happening. The friction of movement, I call it sliding. Some people call it dynamic to give it a fancier name, but it's the same idea. Those are different. So static friction is when 2 surfaces are thinking about sliding and trying. Sliding friction is when they're actually doing it. And those frictions are different in a couple ways. First off, the static friction between 2 surfaces is typically a little stronger than sliding friction. Static friction, furthermore, is adjustable. And let me see if I can get this to work for us. I am going to put blocky in there, okay? And what I want to show you is that I'm going to begin pulling with a spring scale here so that you can see that I'm actually doing it and how hard I'm pulling. This is in newtons. And as I pull to the left, the table exerts a force to the right that exactly cancels my pull. Wow. If I pull with 2 newtons, the table pushes rightward with 2 newtons. If I pull with 4 newtons, table 4 newtons. It's clever, not, I've known people that aren't as clever as the table, but you get the idea. It's adjustable. So static friction, which is the friction between 2 surfaces that are not yet sliding, varies. It picks whatever force it needs in order to stop the onset of sliding. If I pull too hard, and I'll probably get there somewhere at the high end of the scale, or I'll go to a stronger, there it goes. I hope you noticed that what happened is I did that. Let me see what I can do it. I need to give it time. What's happening is a sense, the little microstructure on the bottom of the wagon, top of the table, are sinking into each other like the bristles of 2 brushes, hairbrushes, pressed against each other. They're actually sort of engaging with one another and getting kind of stuck in each other's way. And then when I begin to pull, those sort of bristle-like structures fight the onset of sliding especially strong. I'm at 10 newtons now, and I'm still not getting sliding to go. 12 newtons. Oh, there it goes. Right at 12 newtons, it started to slide, and now I can't get 12 newtons anymore. While the sliding is occurring, I'm only getting 10 newtons. So what you take away with that is first of all, static friction is adjustable. It does whatever it needs to do to start to keep things from sliding. But it's got a maximum. It's got a limit beyond which it goes, forget it, I can't stop this anymore, let her rip. And it's like taking two hairbrushes into each other. You pull initially, they're all interdigitated, they won't go. And then eventually, you begin to pull them through each other. Or toothbrushes. This is something to do with your roommate's toothbrushes. Okay. I'm thinking of the little kid who's caught putting back his father's or her father's toothbrush after brushing the dog's teeth. And the father says, "What do you think you're doing?" And she says, or he says, "I've always put it back, don't worry." Every time I put it back. What can you do? Anyhow, so they're interdigitated like that. Once they get started, they go more easily. And so what you're seeing with the static friction is that it's got its peak value, the strongest it can fight the onset of sliding, is typically bigger than anything sliding friction can exert. Once the sliding happens, the bristles are essentially bobbing along on top of each other. You get a weaker force. That's not always true, but it's usually true. So it means and you've experienced this, getting that file cabinet moving for the first time, you got to give it a mighty shove to get it going. But once it's going, hey, it's easier. Is this vaguely familiar, I hope? All right. Once it's going and sliding friction is there, the force is no longer very adjustable. It's pretty much a steady value. For this wagon with the blocky kid in it, it's about 10 newtons. See, I got all the way to 14 before it started. So now I'm at 12, 10, 11. I'm keeping it moving at constant velocity. I have to pull 10, 11, give or take. But to get it started for the first time, I had to pull extra hard. So that's one observation. This actually, and I'm not going to present it again, that question about the skidding your car wheels, should you or should you not to accelerate the fastest? The reason you don't want to skid your car wheels when you're pulling out at a green light is because as those wheels spin across the pavement, they're experiencing sliding friction. Bottom of the wheel, top of the pavement are moving across each other. You're getting the force of sliding friction, and that's weaker than you can get by getting static friction. If the wheel does not slip, even though things are moving, it's actually engaging the surface of the pavement. I call it touch and release. It's landing. It's not sliding. It's engaging. It's getting traction, and then it rolls and lifts off. And while they're engaged with no slip, it's getting the maximum, potentially the maximum that static friction can give you, which is bigger than you can get if they're actually sliding. Is that okay? Takeaways: skip the sliding. You knew that already, but now you know why, maybe. The other thing is that once you begin to get sliding friction, you get damage. The surfaces, not only are they're chewing up energy. Sliding, I should say now to this view graph here, sliding friction makes some of the energy involved in the story disappear. That is not true of static friction. In static friction, because the two surfaces do not move relative to one another, they don't do work on one another that vanishes the way I did with the sliding box. If I'm pressing against the table and nobody's sliding, I can't move the table can't move me, we're stuck, no work is being done. So whatever energy is around is still around in the same form it started, essentially. So that would imply that static friction never involves any work done by anybody. That's not quite true. If I take an object that's a little less, okay, we'll come back to this guy. To hold a cylinder like this and support its weight vertically, it's not a support force. I am experiencing support forces, but those are all horizontal. I'm pushing against the cylinder is pushing back on me, that's all nice and good. But I need to support its weight, I need an upward force on it. That force, it's got to be along the surface of the cylinder. It's a frictional force. If you grease this sucker, I cannot hold it. You know, it just goes right through my fingers. So I need a frictional force. And right now I'm doing no work on it, it's doing no work on me. But if I lift it, I'm doing work on the cylinder with the help of a static frictional force, and the cylinder is doing negative work on me with the help of a static frictional force. So we are exchanging energy using static friction as the vehicle as the force involved. But no energy is being wasted. All of it that went in comes out. If I let things slip, like this, I'm working my way up the cylinder. Uh-oh, that was sliding friction. You okay with that? I mean, I can do it up here. Right? Up sliding friction, that will have wasted energy. It will have done negative work on me, and I will not have done positive work on it. The energy disappeared. Well, it didn't. It became thermal energy. So, but takeaway so far again, that static friction, you can use it to move to do work, but it doesn't waste the work in thermal energy. That all the energy that goes into the motion is still apparent. You can still follow that energy. Work was done. Sliding friction gets rid of it, wears things out. I got started on the bristles brushing across each other, and then I got distracted by my own random ideas. Those collisions really do wear stuff out and break off pieces and stuff. And you've seen this all, the wearing, for example, of staircases going into buildings that are frequented. Even stone will eventually wear away because of all that scuffing and stuff. Your shoes, you know, why do you have to buy new shoes other than the fashions changes? Because if you perfectly pick up your feet and land them, you get only static friction the whole time. Life is good. But if you're like any normal person, you're there kind of scuffing along, you're wearing the bottoms of your shoes out. You're just shaving off material with every collision. All right? Well, that brings me then to this, to kind of a recap on the first of the conserved quantities. We're about to hit two more. The first of the conserved quantity is energy. And it's conveyed by doing work. At least that's the mechanical means for transferring it. There is the thermal means, which we'll leave aside, but that's for the other semester. But just to sort of recap all the possible forms of energy, kinetic, that's the energy of motion. So anything that's moving has energy in its motion. It's indifferent to the direction of the motion. So energy is not about going somewhere. It's about having the ability to do things, ultimately to do work. And if you're moving, you got the ability to do things. We don't care about which direction you're moving. The other ways in which energy can be around are potential energies. So they're energies stored in the forces between or among or within things. And we've seen gravitational. So if you lift something upward, you know, as I lift this guy upward, it has more and more energy stored in the force of gravity between it and the earth. We give all that energy to the ball and say that it owns that energy. It's got more now than it had before I lifted it, and it can do things like it can turn that energy into kinetic if you just let go of it, let it be a falling object. So gravitational we've seen, magnetic. You know, some years I bring up some strong magnets and let them jump at each other, but you've certainly seen that magnets that are separated by some distance, if things are right, we'll learn down the road what it means to be right, have them oriented properly. They'll leap at each other. So they were motionless before, and suddenly they're moving. Where'd that energy come from? That energy came out of energy that's stored in their magnetic interaction, and we'll learn a lot more about that, probably more than you want to know, in coming weeks. But that energy can be released, and you can call it magnetic energy. It'll ultimately be called magnetostatic energy. It's the energy just in presence. Without motion, you just have energy between magnetic poles. Elastic energy. All right, you guys who were here last semester, you've seen this guy. I hope you had a can like this. Want some nuts? It never gets old for me, except it gets old for me, not really. But, I had one of these as a little kid, and my grandfather would come up and, "Hey, Grandpa, you want some nuts?" Yum. Ah! Surely you've seen this, or there's probably an app that does this now. So It's really lost. So this is energy. There was energy stored in this, apart from the pretend nuts hiding out. And the energy was stored in the elastic. It's a spring in there, and the compressing the spring involves doing work, right? I have to take the two parts and I shove them toward each other, and they move toward each other. I'm doing work on them. I'm packing the energy in, right? So the act of stuffing that snake in the can, put the energy in. It's in there, potential energy, you know. And we could do it again, but I won't. Okay. So that elastic potential energy. There are lots of that. Clocks portable clocks used to store energy in what form? In elastic, in a spring. They had a mainspring, which was an energy storage device. This is so far, this is almost before my time, not quite. Wristwatches, you actually had to wind them up to store the energy. Actually, they've all come back. That stuff's back, but it's like the boutique. It's for men who don't know what, man jewelry, right? It's these fancy watches that are almost as accurate as a Kmart $3 watch. But cost $100,000. They store energy in a spring. Electric energy. Well, batteries. You've seen batteries storing energy your whole life. But this maybe not so much. This is a device that we'll become familiar with, I don't know, I can't predict exactly when, but a couple weeks. It's what's known as a capacitor. Although it looks like a big blue cylinder and nothing else, it actually contains two surfaces that are exquisitely close to each other but not electrically connected. Story about how that's done is complicated, but basically it's you can visualize it as two sheets of metal separated by a gap that's insulating. And you can put a lot of positive charge on one surface. Remember positive and negative charges? Hopefully we'll do those also. They are the famous opposites attract charges. Positive charge here, negative charge there. They love to get together. So you put them on these surfaces, positive on one, negative on the other. They would love to get together, but they can't quite get to it together because they're separated by an insulating gap. And you can put an incredible number of them on the surfaces in this device because they're so close that attraction helps pack them in. They hate being near each other. The positives hate being near the other positives. And by themselves, just all positives, they would be fighting it out and trying to get off my hand. But by bringing the negative over here and putting it really close, they go, well, this is good enough. I'll hang out here because I see that lovely negative across the way. And you can get a lot of them on there. The long and short of it is, I can get a huge number of positive charges on that side and a huge number of negative charges on that side, and they're desperate to get a little closer together, and we'll let them. But to do that, I can't do it by hand because I can't, no electric charge tweezers. So I'm going to use another stored form of energy, which is the energy stored here in these batteries, put in by the manufacturer, mostly in making zinc metal, pure zinc metal. So these batteries store, most of the batteries you encounter store the energy in some metal. Zinc or lithium are the most popular at present. So it's stored mostly in zinc here. And I'm going to use that energy to let the battery move the charges for me. So it's going to pile up a whole lot of negatives on one side, positives on the other, and it actually takes time. It's not like in a microsecond. It's probably pretty well done now, but it's been moving them. The batteries are consuming their energy. They're actually, this gives them a significant hit on their lifetime total energy. All right, so hopefully I've done that right. So now I've got positive on this side, negative on that side. I'm going to give them a route home to get together. And if it works, expect a good pop. Ready? Get set. Again? Yeah. Yeah, now you know what to expect. This, incidentally, is how some welding systems work. That was a huge amount of energy that was released in that short period of time, and it melts the metal. Okay. Okay, so I'm letting the batteries do their trick again. By separating those positive and negative charges, they want to be together, pulling them apart, stores energy them in, we'll call it electrostatic potential energy. It's in the energy, it's in the forces between these charges. And they're pretty well all happy at this point, wishing they could get a little closer together. When I do this, I'm sort of set things up for our future. We've got the positives on one side, negatives on the other. We're creating a path of conducting material. This former screwdriver carries electricity reasonably well. Ready? Get set. Some people have tried to take a picture of me doing that with my eyes still open. I couldn't do it. You can't not blink. It's just hopeless. You can try it after class. All right. There's still some more oomph left in these batteries. Okay. Chemical potential energy, chemicals, allowing chemicals to rearrange, various collections of atoms and molecules to rearrange. They have energy available often in their chemical bonds. If you allow, for example, oxygen and hydrogen to get together, they love it. They stick like crazy. They release a lot of energy. They do work as they draw together and stick. And so the energy comes out. Nuclear, I don't have a good demonstration for that either. I mean, actually, we do at the end of the semester. Little nuclear things coming apart, not big ones, right? Too much trouble. Also, painful modern life. So where does thermal energy fit into this? Thermal energy isn't different from these. Well, no, it is these. Kinetic energy and those potential energies. It's the same stuff. It's just little tiny pieces of it sprinkled around randomly or statistically among all the atoms and molecules that make up a surface. So when you rub your hands together, an activity which involves work, typically done by, say, the muscles in your arms and shoulder, that energy is vanishing. No, it's ended up as thermal energy in your hands. The surface has got hot. And that energy consists of that atom moving a little faster than usual that way, bumping into that atom a little more aggressively and experiencing a little more stored energy. It's all the jittering motions become more extreme. Believe it or not, there's action going on. Every molecule and atom in this room is in constant motion, jiggling around and bumping into things. There's energy associated with that jiggling, and it's thermal energy. Okay? Because I can, just to point out the old-fashioned way of starting a fire. A piece of wood with the bowstring wrapped around it, I can make that wood spin in a socket, and if I do this right, I'm clearly going to be doing work. I'll push it as it goes in, as it goes towards you, and it will move toward you. I'll pull it as it moves away from you, and in both cases I do work, and hopefully that work will be turned into thermal energy and make this guy smoke. Oh, come on. Can you see smoke? I saw smoke for a minute. Come on. Yay! All right. Sometimes I manage, sometimes not. Okay. Not the greatest way to start a fire, but the concept works. Clearly, taking ordinary work, crushing it up, and making thermal energy out of it. The reason thermal energy is different is because once it's been chopped up and distributed randomly, reassembling it, getting it back together to do some useful work becomes very difficult, in fact, statistically impossible. It's like breaking a vase. The whole thing's still there. You smash on the floor. It's all still there, just like all the energy's still there. But now if you want to come back together and become a vase again, you're going to be dropping it a lot of times before you manage to get it to reassemble. As an example of that, we should be looking down on a collection of beads, purple on the right, white on the left. This is a very orderly arrangement of those beads. This does not happen by chance. When I didn't do this, but when Al did this, he put them in carefully. If I allow them to get more statistically distributed, they will not look like this. How do I do that? Well, I just look away and stir. Ready? Stir. Okay. I'm not cheating, see? Wow, randomly distributed. How many times do you think it would take me to stir them again and have them separate out, purple on the right, white on the left? A lot, right? I'll try. One of these days I'll do it, and it'll be purple on the left and white on the right, pure, and I'll go, oh, what a disappointment. No, it's never going to happen. Not because the laws of motion forbid those beads from segregating out perfectly. Purple on one side, white on the other. The laws of motion don't care. The reason it doesn't happen is because it's so statistically unlikely. It's like rolling dice, rolling 100 dice, and they all come up ones. Like, wow, it's not going to happen. Rosencrantz and Guildenstern are dead. Is this familiar? Flipping coins, and it's always heads. It never happens. Okay, so this is the same situation with thermal energy. When thermal energy is created, it's chopped up and randomized. A concept associated with, you've heard the term entropy, which is the measure of disorder in things. Disorder is never decreasing. So once you create disorder, it's very hard to undo it. The only way you can undo it is by exporting the disorder. You make a big mess, you can't fix it, you can throw it away, export it. So that's the nature of thermal energy. It is energy. It's the same old energies, kinetic, potentials, all that. It's just lots of little pieces. You can't do much with it most of the time. The rules governing it are interesting, but beyond this semester. So sliding friction is a problem because it creates thermal energy out of ordered energy. So minimizing it is part of the goal of, and I can go back to part of the purpose of wheels. Oh, so, okay, so I'm going to skip that. Let's see. What do I do? Let me just show you how wheels work so I don't get tied up in first off, the simplest way of getting rid of the sliding friction problem. I'll get the kit out. Well, I'll put the kit in because here this is a lousy plan for a vehicle trying to go any distance. Without wheels, it's going to be doing a lot of skidding and a lot of energy waste. I mean, you can drag a sled on pavement. Huge amount of thermal energy created. So the simplest, probably one of the most ancient solutions, is to lift the sled up on rollers. And now, those rollers, having block in there is just a pain. Those rollers eliminate sliding friction. They do not eliminate static friction. Static friction occurs whenever one of those rollers touches the wagon or touches the ground. They're in contact, and if there's any tendency for movement between those two surfaces, there will be some static friction. But that's okay. It doesn't waste energy. It is actually involved in getting those rollers to rotate. If there are no friction forces at all between the wagon, table, and rods, they wouldn't begin to roll. What would exert the torque on them? So they need the static friction in order to roll, but they're not sliding. They're landing and leaving. On a larger scale, just make sure it's clear to all of you what I mean by that. Let me identify. That spot, do I have any marks on it? No. That spot on the rubber is not in contact with the ground yet, but it will be. There it is. It lands, it's landing, it's lifting. It never skidded. It just landed and lifted. So it's always a static friction effect there. And static friction is just not a problem. Same thing's going on with these rollers. They're landing and leaving as they go. So that's all good. It's still not a great recipe for a vehicle. You're never going to find one at the local car dealership that runs on rollers because the rollers keep popping out the back and you have to keep putting a new one in. Not very, if you're desperate, you're trying to move some monolith to Stonehenge or something, you can do it. All right? Rollers. A more sophisticated solution, let me give those pictures. So the roller's under the file cabinet there on the left. It's perfectly feasible if you've got a short distance to go and you've got, it's okay. It's just not a long-term solution. Second part of this picture that's of value is the old wagon wheels. Let's pretend this is a wagon wheel. The way a wagon wheel would work is it would have a fixed axle, bolted onto the cart. It would shove that axle through the center, what's known as the hub of the wheel, and there's the wheel sitting around this hub. And as you move the wagon forward, pulled by whatever, oxen or something like that, static friction between the wheel and the ground caused the wheel to rotate. It produced a torque that made the wheel rotate. But there was no sliding friction here. That's great. You've gotten rid of the sliding friction. Almost. In the old wagon wheel approach, by putting a wheel on the wagon, getting it up off the ground, you got rid of the touching the ground sliding friction. Where the wheel touched the ground, there's no sliding friction. It's static friction. It's touch and release. There is, however, friction between the axle and the hub in the old-fashioned wagon wheel. Right here, that axle is motionless, and around it is this donut hub, and the two are rubbing across each other. You okay with that idea, that they're rubbing? What's the solution? Well, one of it was axle grease. The reason this doesn't have a pot here, but some of the old wagons, if you go look at the old covered wagons, they would have a pot to be filled with grease, lard or something like that, so that you'd put into this junction to try to reduce the friction. You're trying to lubricate these two surfaces going across each other to get the friction down, because they do produce thermal energy and wear things out. This all caused wear. There's a reason you had to get new wheels occasionally. But part of the solution was to make that hub and axle as narrow as possible, so the actual movement was small. Yeah, you're fighting frictional forces in there, but make the distance small. Remember, work is force times distance. Make the distance dinky by having a little teeny hub that doesn't move very far each time the wheel rotates. So little hubs were valuable. The better solution was to go back to rollers. Insert rollers between the axle. This is the axle. It's the same story here. There's the axle. There's the hub on the outside. And put rolly things in there. They're either rollers or they are balls. And they roll around, and you're back to all static friction, no sliding at all. And I've got a couple of examples of these sorts of bearings. I can come back to this. Okay, so now we're looking down here at my hand, yay. And here is an example of a ball bearing. The middle piece is where the axle goes. The outer piece is where the hub goes. And between them are these balls that roll. Can you see that? These are, they're old technology, but they revolutionized the world. You guys have ball bearings in so many of gadgets. Your car's full of these things. Bicycles. Any gadget that has something that moves, they're all full of bearings. I have somewhere, oh, here it is. Here, that is literally a ball bearing, because it's balls and it's bearing the load. This is a roller bearing. So it's a whole bunch of rollers that go around. So you put the axle in the middle there, you put the hub on the outside, and the little rollers roll around and get rid of this sliding friction. All right? Last thing to point out. Yeah, too many gadgets. Now you're looking at nothing. There we go. Just to show you that there are two types of wheels, two categories of wheels on vehicles. Free wheels and powered wheels. Your car has typically 2 free wheels, 2 powered wheels. Exceptions would be there are some cars that have all-wheel drive, 4-wheel drive. Bicycles routinely have 1 free wheel, 1 powered wheel. What's the distinction? A free wheel, which you have on the front of a bicycle wheel, is a free wheel. It's a wheel that spins freely relative to the vehicle itself. And the only thing that can possibly make it rotate is the ground pushing on it by way of static friction, causing it to rotate. So this is a free wheel. When you're on a bicycle, you're here. There's the powered wheel. We're going to head to the right. The front wheel is the free wheel. When you move right, it begins to roll. And the force that causes it to begin to rotate in order to roll is actually friction from the ground. The ground tries to stop the bottom of the wheel from skidding, and it does that by exerting a frictional force on the bottom of the wheel opposite the direction the wheel is trying to go. You're trying to make the wheel go forward, that is to your right, so the ground pushes to the left, and that causes this rotation, like that, clockwise from your view or equivalently away from us, according to the physicist's language. So free wheels are turned by the ground. A force, the act of heading forward causes the ground to exert a torque on them and make them rotate. The other possibility is a powered wheel. The rear wheel on a bicycle is a powered wheel. Typically the front 2 wheels on a car these days, front-wheel drive, are powered wheels. In a powered wheel, things are a little different. What makes the wheel spin is not the ground. It's the engine, or you. You twist the wheel and make it spin. So you're providing the torque that gets it going. What does the ground do? The ground actually applies a frictional force that tries to keep the wheel from skidding as the engine twists it. If you greased the ground, the wheel would spin wildly across this pavement. So get rid of the grease, the pavement and the wheel grip each other, and as the wheel begins to rotate because of the engine, the ground begins to push on the wheel in the forward direction. The motivation for why should the ground push the bottom of the wheel at all is to keep the skidding, keep from sliding, keep from relative motion. And so if you twist the wheel, and the engine twists the wheel this way, clockwise, and as it does, look what's happening at the bottom of the wheel. If they weren't in contact, they skid across each other. So the ground and the wheel are going to fight each other to not skid. And they do that by having the ground push the bottom of the wheel to the right. In this case, the ground pushes the wheel in the direction you want to accelerate. The purpose of that push on the bottom of the wheel is to keep the skidding process from starting. That's good. Skidding doesn't start. But that is the only horizontal force on the whole vehicle, is that forward push of friction. That's what makes the vehicle accelerate forward. So how to summarize this? Free wheels turn because the car heads forward. The car heads forward because the power wheels turn. As the power wheels turn, they grip the ground, summon a frictional force out of the ground to fight skidding, and that frictional force in the ground not only fights skidding, but it pushes the whole car forward. So that's how you propel yourself in a car or in a bicycle, is the act of trying to making the powered wheel try to skid. All right, we'll call it a day. Have a good weekend, and see you on Monday.